Today, at least to start, about a manifold of bounded negative curvature. So the definition is it means that the curvature is bounded between -1 and some constant, so it's strictly smaller where a is not 0. So it's strictly bounded below. And everything is a bit simpler in this content. And later we will, everything we do here, we aim to do later for a manifold of non-positive curvature. And there we will pay some price. One price is that everything will be more difficult. Another price is that we will have to assume that the metric is analytic. The manifold is analytic. But now we don't need even to assume that. Of course, it should be C2 or at least, because otherwise we cannot define curvature. But and the exercise I want the expert of you to think of is why do we really need strictly negative? Why do we need this A? Why can't we just say that the curvature is less than 0? Where will I need it? And recall, I studied the thick-thin decomposition. But you know, maybe today we even restrict to the subcase of symmetric spaces of rank 1. So somehow a main example of manifold of negative curvature are symmetric spaces of rank 1. In that case, the curvature is bounded between -1 and -1/4. And the example are the hyperbolic spaces, the real hyperbolic, the quaternionic hyperbolic, and so on. The complex hyperbolic. And there is one more example. So there are like 3 family and one exceptional example. For those of you who know the classification of rank 1 simple group, did we discuss this in the midrasha this year or no? But hopefully maybe we will. But anyhow, you should think of real hyperbolic, but like the nicest, because then the curvature is identically -1. But everything we will say will be valid for the more general class of. So here the metric is analytic, and it's much more than that. So the group of isometry is a simple Lie group. But everything we will say will apply here in this context. And the thick-thin decomposition I discussed last week. Maybe today I will have time to prove it in the second hour. But first, let's state it and use it. So it says that given D is the dimension, there is epsilon, which is called the Margulis constant. And such that if M is a D-dimensional manifold complete, I always assume a complete Riemannian manifold of bounded curvature so bounded, I always mean that. And this is the -1 is fixed. A can be changed, and I think epsilon does not depend on A. So if M is d-dimensional, but let's fix also A. D-dimensional complete manifold of bounded negative curvature and finite volume. Then you can write M as a union, M bigger than epsilon, union M smaller than epsilon. Okay, they have a non-trivial intersection, which is lower dimension. If you don't want intersection, then you replace one of the inequalities with strict inequality. But this is somehow nicer because then this will be a manifold with boundary, and so sometimes there is advantage to that. Sometimes you want strict. It doesn't matter so much. Such that M greater than so you remember the definition of the thick part and the thin part. This is the epsilon thick part, this is the epsilon thin part, and the point was that the connected component of the thin part are of two types, two possible types. I mean, it could be that this set is empty for some manifold, and it could have only one connected component or two or more. But what are the types? There was a cusp, and this is homomorphic to n cross a half line, half loose, where n is a compact manifold of dimension 1 less, d-1. So that's a cusp. This is what we sometimes draw like this. It's unbounded, but its boundary is the manifold of smaller dimension. And the second type is a tube, or a tubular neighborhood of a short geodesic, and it's homomorphic to a ball bundle over a circle. It's a ball bundle over a circle, so when the ball is of dimension, again, d-1, so you should think of a product of a ball and a circle. In dimension 2, we draw it like that. So there is a short geodesic in the center, and it's a neighborhood, it's tubular neighborhood, and here the ball is one dimension, so it's a segment. So this is segment times a circle. In higher dimension, it will be slightly more complicated. And one need to be, if you want to be completely precise, you need to also either consider the case that a thin component consists of a single geodesic. Maybe there is a short geodesic whose length is exactly epsilon, so it has no neighborhood in the thin part. But if I do here strict inequality, it will not happen anymore. And otherwise, I could slightly change epsilon. For application, it doesn't matter so much. So I may perturb a bit epsilon for a specific manifold, so that this will be correct even with that. But in general, there could be geodesics of short closed geodesic of length exactly epsilon, and then Okay, so what do we learn from that? So I will prove it, but before that, let's derive some application.
What do you mean for a manifold? You mean for a D, you can take a small epsilon so it won't happen? Or?
So if for a fixed M, it could happen that there is some epsilon, some short geodesic of exactly length epsilon.
But if given D, can you choose epsilon small enough so that it won't happen to any M?
No.
Okay.
I mean, no. But sometimes, because of some data, for instance, suppose we consider only three-dimensional hyperbolic manifold. So I know, because of other stuff, that the length of a geodesic must be, with certain parameterization, the length of a geodesic must be an algebraic number. So if I choose epsilon to be non-algebraic, it will never happen. So you can do. But if I consider all two-dimensional hyperbolic manifolds, you cannot. You can find for any epsilon you choose, you can find a manifold of exactly that, due to Teichmiller theorem. But let's see the consequence. So first, a remark. So the picture that we like to draw sometimes is it's two-dimensional, and here there is one cast. And here there's one tube. So you see there are two components. Also the thick part has two components. But in higher dimension, so if D is at least 3, the thick part is connected. And in that case, it's a connected, compact manifold with boundary. So why is that? Why it is connected? So I will not prove now that it's a manifold with boundary. We will see it later. It's actually not completely obvious. I mean, it seems obvious. The intuition seems obvious, but the proof requires some stuff. But to see that it's compact, it's easy, because at any point here you can put a ball of a certain radius, such that you can take a maximal epsilon discrete set and take balls which will be of epsilon over 2 diameter, which will be all disjoint. And since the volume is finite, you must have finite remainder. So since it's closed and the entropy is finite for every epsilon, so it has is compact. But why it is connected? So this follows from that. The cusp, suppose you have two points here. So I want to show that I can move from one to another inside a thick part. So, okay, suppose I cross a cusp, then you can deform this to since a cusp is homomorph, you can deform the cusp to its boundary, then you can find a path which stays on the boundary.
But this is true also in dimension.
Yes. This is true also in dimension 2. But in dimension 2, you cannot cross tubes. But in higher dimension, you can cross tube. Why? Because if you don't need to cross tube, because the tube is a ball bundle over a circle. What is the boundary of a tube? The boundary of a tube is a sphere bundle over a circle. And the sphere is of dimension d minus 2. If d is 2, d minus 2 is 0. So the sphere of dimension 0 is just 2 points. It's not connected. But if d is 3, d minus 2 is 1, then the sphere of dimension 1 is a circle. If d is larger, the point is that spheres of positive dimension are connected. So the boundary of every thin component is connected. So suppose you move from one point to another and you cross a thin component. So instead of moving inside, move on its boundary. So you stay in the thick part. Okay, so the thick part is connected.
So this isn't exactly true if you take slightly smaller than epsilon, right? I mean, it's the interior of a ball bundle of those.
Yeah, it's if you want, it's a open ball. It's a bundle over a circle, and the fibers are open ball. But if I do it like that, it will be closed ball. And and I prefer somehow to do it like that usually, but then there is this small issue I mentioned, but it's not a real issue. Just,
Is it still a symmetric space?
What?
Can it still be a symmetric space?
Sorry?
Can it still be a symmetric
What?
space? The thick part.
No, you mean as what do you mean? No. The symmetric space is a universal cover.
Okay. So
Uh,
it has to be the
Yeah. So the manifold is a quotient. It's locally symmetric, and the thick part is even worse. It's a submanifold with boundary.
So it's not locally symmetric.
It's in a sense in the interior it is. Every point, of course, if we started with a hyperbolic manifold, this will be a hyperbolic manifold with boundary. So in a sense, but
It's not complete. I think we said that Alex was not really
It's complete.
no,
It's not complete,
the point is that there is a boundary now. There is a boundary. It's not locally symmetric because here you don't have a neighborhood. It's not even a manifold. It's a manifold with boundary. So the thick part is a manifold with boundary. Okay, so let me now. So here is a theorem. Basically, the case where M is hyperbolic was proved in a paper by me with Alex Lubotsky, Mark Burger, and Shachar Moses in 2002. And the general case approved later. So if you don't need even that. Yeah, okay, let's suppose that D is at least oh, okay. Okay. The theorem is that pi 1 of M is isomorphic to pi 1 of R, where R is some D alpha volume M simplicial complex. So I remind you that the simplicial complex is dV simplicial complex if the number of vertices is bounded by this.
Wait, what is
The pi 1 of M,
R is
where is okay?
where R is
where R is some dV simplicial complex. And let me prove it to you. And let's assume D is at least, the dimension is at least 3 again. Let's assume that the dimension is at least 3, because in dimension 2 basically we are considering hyperbolic surfaces and we have Gauss-Bonnet and we know much more. So it's so in dimension 2 everything is, say, in some sense obvious. We know everything. So we suppose that. And then actually the proof, so here is a proof, but it's not a real proof. It's a false proof. And one exercise for you is to find the mistake in this proof. I mean, in the gap in it. So first, we say that pi 1 of M is isomorphic to pi 1 of the thick part. That's the first step. And the second step is that pi 1 of the thick part, or not even pi 1, the thick part is homotopic to R for some D alpha V simplicial complex. that's the two. Okay. So why 1 is 2? Because no, sorry. This is even false. This theorem is not true. Assume that D is at least 4. Yeah. Suppose D is at least 4. If the dimension is at least 4, then we have that. It's not true in dimension 3. So
Then
and
the other
if-
D's.
what?
The other D's.
Yeah. Yeah. Okay. Maybe.
Dimensional guy.
Yeah. Maybe if for if n, then if the dimension. Okay. Okay. I will not use the dimension anymore, anywhere except in the statement. So if the dimension is at least 4, then for some d alpha p, where the constant d and alpha depend on the dimension.
So here you can assume M is just bounded negative curvature.
Yeah, I assume that yeah, this is true in the case of bounded negative curvature. Yeah, if you want the most general version of it for bounded negative curvature, it's written in the recent paper of myself with Uri and Roman. The first version for hyperbolic manifold is in the paper with Lubotsky, and Moses. Okay, we will see a proof. We will see a complete proof of that. Okay, so 1. So let's proof of 1. So we know that M is M greater than epsilon union M smaller than epsilon. Suppose this, so this is several components, right? So I can write them, I can add them one by one. So M less than epsilon, I can write them at M less than epsilon 1, M less than epsilon 2, M less than epsilon k. So there are only finitely many components. By the way, the number of components is bounded by the volume. So this maybe I will explain in a minute. The number of components bounded by the volume. Basically, okay, let's say it. At the boundary of each component, you can put a small epsilon over 2 ball, and this ball will be disjoint. So you see, you cannot have too many components. So there are finitely many components. And to add them one by one. So I claim that pi 1 of M is isomorphic to, or let's say pi 1 of M greater than epsilon is isomorphic to pi 1 of M greater than epsilon union M smaller than epsilon 1. I add the first component. Why? If and so on. So I will add them. I will add them one by one. Then pi 1 of M less than epsilon union M thick part union 1 thin part union 2 second thin part, and so on. After k steps, I add all of them. And in each step, what do you glue? Each step is by Van Kampen. So let's do this step. So by Van Kampen, pi 1 of m greater than epsilon union m less than epsilon 1 is the same as pi 1 of m greater than epsilon amalgamated product with pi 1 of m less than epsilon 1 over the fundamental group of the boundary. Right? Okay. So, but what is this? So if it's a cusp, then this and this are the same thing, because there is a deformation retract from the cusp to its boundary. So in the cusp case, this is obvious. In the tube case, so suppose this is a tube. I will not write that in the cusp case it's obvious. It's very obvious. But in the tube case, this will be Z, because it's a ball bundle over a circle, and this will be Z, because it's a sphere bundle over a circle, and the sphere is of dimension d minus 2. The dimension is at least 4, so the sphere is of dimension at least 2. A sphere of dimension 2 is trivial fundamental group. So this is Z and this is Z, and if you think about it, it's the same Z, so they cancel each other. Okay? Now what happened in dimension 3? Just a remark. In dimension 3, in the case that this is a tube, here we will have Z, and here we will have a S1 bundle over a circle, so we'll have Z square. And this Z square will not cancel with this Z. It will add some relation to the fundamental group. So we can still learn something about this, about fundamental group of hyperbolic manifold. We'll discuss it at some point, not now. So this equality says also something in dimension 3, but for later.
But can you explain again in dimension 4 why it's exactly Z and Z?
In dimension 4,
This is Z. Why is the boundary Z?
the boundary is a sphere. In dimension 4, it's a S2 bundle over a circle. S2, if you think about it, if you S2 bundle over a circle, it's exactly
Something
the same
simply
circle.
connected over a
Yeah,
circle.
and it's exactly the same circle, so it's exactly the same. And okay, let me just give. You are suspicious because I told you that there is a mistake, but it's not here. This is true. I mean, of course, you should think about it. You should meditate until you understand all the details here. But this is true. This is also the other part is true. But so here is the mistake. The mistake is in number 2. Not a mistake again. But it's not exactly proof. Number 2, what I would like to say. So this is the proof of 1. And the proof of 2, basically, I will say we did last week, 2 weeks ago. You remember the heuristic we did 2 weeks ago? We discussed. We said, suppose we have a manifold, which is thick. It has epsilon thick. Then it's homotopic to a dV simplicial complex, because you take a maximal discrete epsilon discrete set, you take the epsilon balls, you show that it's again you don't work with epsilon but with epsilon over 4 for some reason, but never mind. But you get a good cover by convex sets. I mean locally convex set, and I mean sets whose lift to the universal cover are convex, and therefore it's a good cover. So by the nerve lemma, the classical nerve lemma, it will be homotopic to the manifold. And this was true, but it's true if it's a thick manifold. And now it's not. Now we have a thick manifold with boundary. And the thick T decomposition, which we always draw very nicely, it's true topologically, but but this picture doesn't tell us enough information on the boundary, and the boundary can be ugly. The boundary, so we draw this picture of a tube with a smooth boundary and a cusp with a smooth boundary, and actually the boundary is not smooth at all. The boundary is ugly, and then you will start to cover you start to do the good covering argument, and in the picture here it seems very nice, but in reality, if the boundary is something like that, so we want to put some ball around this point and another ball around this point, and then suddenly they will intersect outside, or suddenly one ball will intersect. Okay. There is some
This
analysis.
shows that why M is not homotopic to R.
Sorry?
I understand why this shows why M is not homotopic to R. Why that doesn't affect the proof.
Sorry? I say that this line needs justification. So M greater than epsilon, and in reality I actually cannot prove this. What I will need to do is to smoothen a bit the thick part. I will replace the thick part by something which is similar properties, but it has nicer boundary, and then we can prove it. So that's what. Okay, so before going into more formality and proving details about the thick-thin decomposition and so on, I want to say that this idea is nice in negative curvature, and it works in negative curvature. Here, my question for you is, yeah, okay, never mind. So it's nice in negative curvature, but I want to do something similar also in non-positive curvature. But in non-positive curvature, we don't have a nice description of the thick-thin decomposition. We can define it as we define it in the negative curvature case. Like the thick part is where the injectivity radius is bigger than epsilon, and the thin part is where the injectivity radius is smaller than epsilon. And we have the Margulis lemma, so we have epsilon. We will discuss Margulis lemma. It's a very general, in very general situation. But what we don't have is the description of the thin part. So, remark, in non-positive curvature, which is the harder case, the thin part is quite mysterious. So nobody really understands it. How many mistakes? What? Why? Which why?
The first one.
Here?
No, no.
No, M-Y.
This?
You know, before the
No,
equals
also.
12.
Here? Oh? Okay, so it's a mysterious one. So the thin part, nobody really understands it. So you cannot do this Van Kampen in non-positive curvature. So we would like to replace this Van Kampen idea by another idea, which maybe we can generalize into non-positive curvature. So here is the idea. So here is another proof of the same statement. So the statement was that pi 1 of m is so here's the lemma. That pi 1 of m is the same as pi 1 of the thick part. And this lemma is we proved by Van Kampen, and I claim. So here is another proof. Again, it will not be a proof because it will rely on details that we'll do later. But here is an idea of a proof that will be applicable in. Okay. So since the dimension is at least 4, if C is a closed geodesic, the fundamental group of M is the same as the fundamental group of M minus C. If I take a manifold and I throw out some circle, I don't change the fundamental group. In dimension 3 you do change. In dimension 2, if you throw a circle, you are not connected anymore. In dimension 1, everything is a circle, but in dimension 2, if you throw a circle, you are not connected. In dimension 3, if you throw a circle, you create another generator to the fundamental group. In dimension 4, you didn't change the fundamental group. Why? Because what's the fundamental group? It's a group of all closed loops. Suppose you have a closed loop that you go into the circle. So it's a group of loops up to homotopy. Homotopy between loop is two-dimensional. It's something two-dimensional. Now the circle is one dimension. So this two-dimensional thing that you homotopy between loop, you have a fourth dimension that you can move out so that it will not touch this circle. So that's somehow explanation by hands why in higher dimension, if you throw, and this also applies more generally. If you look at the higher homotopy groups and you have higher dimension, so it's a reason in 4 dimensions. So that's a simple algebraic topology covering theory. So now, so the idea is the following: whenever you have a tube, in every tube, we can throw out the central geodesic. So every tube is a neighborhood of a short geodesic. So throw it from the manifold. You have this tube, and you have this manifold, this geodesic inside, and you throw it.
What is M now?
M is some manifold of a negative curvature, strictly negative curvature, bounded negative curvature, and I want to say that the fundamental group is the same as the fundamental group of the thick part. So the picture, the thin part is component which are cast, which I don't care much about because at least in this argument I don't care about them because cast I can throw the cast, I can deform the cast to its boundary, so I don't change the fundamental group, I can ignore this part. And here I have some short geodesic that if I throw it, I don't change the fundamental group. Okay, because the dimension is at least 4. Now, if I throw this geodesic, I claim, I will prove in the future, that there is a deformation retract from what left to the boundary. Somehow, every point I will have a preferred direction that will, if I go in this direction, I will increase the injectivity radius. I will get closer to the thick part. So I have some deformation retract here at every point. The only point that I cannot define it is here when the short geodesic I don't know to choose between right or left. So here I don't know to choose, but at any other point I can choose. So if I throw this, I have a deformation retract to the thick part. And so this is an idea which will be made rigorous later. So with no proof here, it's just an idea. We control the central geodesic and then deform what left to the thick. And this idea will actually work also in non-positive curvature. In that case, we will not throw a geodesic, we will throw something more complicated, but a submanifold or a union of submanifolds.
But we won't have tubes in the.
We don't have YouTube. We will not understand what we deal with, but we can still do this process. So we will have something. We will define some Morse function, and we will choose the critical, some singular submanifold, and then do some Morse theory. But we will get to that. The main ingredient in all this is the Margulis lemma. It's what allows us to do the 6 in decomposition, and it is also what will allow us to do this deformation. We will show that. Okay, so we will discuss very soon the Margulis lemma. So this is basically somehow. This could be the end of the introduction to the course, or I could also continue about the introduction, because so far we had a very nice. I think we have nice conjecture, nice hopes, but the main idea is to decompose the manifold to thick parts and control the complexity here by good covers. And we need to somehow smoothen the boundary and justify things, and to do and to try to do some analysis in the thin part by either understanding it topologically or using some Morse theory. But then the information that we gain from this procedure is limited, because we cannot get any information further than bounding the complexity by the complexity of the thick part. But maybe the thick part is much simpler than what we imagine. We imagine the thick part somehow like a simplicial complex, a DV simplicial complex. But in certain situations, so this is true. In most general situations, you cannot say much more about the thick part. But in many situations, you can say more. You can say that the thick part must be almost everywhere. Not just epsilon thick, but I mean really thick, like 1,000 thick or 1 million thick, depending on the volume. So this is somehow the in recent year this was realized, and this is the notion of Benjamini-Schramm convergence, which was borrowed from graph theory to the theory of manifolds. And the tools here are the invariant random subgroups and rigidity that will allow us to understand manifold of very large volume. So for manifold of very large volume, we can say more. We will not in all situations, but for instance, if you consider higher rank manifold. So this 16 decomposition idea will tell us that the first Betti number is bounded by the volume up to some constant. This was the Gromov theorem. This new approach of Benjamini-Schramm convergence and invariant random subgroup will tell us that actually the Betti number divided by the volume will go to 0, and even quite fast when the volume goes to infinity. So if you will take manifold of larger and larger volume, the first Betti number will not be linear by the volume, it will be sublinear. But we will get to that. This is some these are new other ideas, and we will get to that later in the course, I think. These tools, I'm just saying this very quickly, but these tools of invariant random subgroup also allow us to get information about not just asymptotic manifold, but also we will see that this idea gives a simple proof, the Margulis theorem, that there is a lower bound of the volume and so on. So it's really important tool in this understanding the complexity of manifold and asymptotic behavior of manifold. And but we will get to that later. So I think it's a good point to stop with the introduction. I could go do all this course just about introduction and be less formal, but now I think it's about time after the break that I will start to be more rigorous. So let's have a break, and then I will prove the Margulis lemma and the 16 decomposition. And